Okay, so for the last part of the course, we have beam theory, which is basically kind of a simple theory. So, and like it's basically a historical theory. So like it was developed way before we developed the stress and strain concepts, which was developed by Euler and Tesenko. And for basically beam theory, there are a few assumptions that the founders have made for this beam theory. So the basic idea for it is to reduce the number of variables so that we can basically easily compute it for like any random arbitrary shaped body, and like we don't have to find the analytical solution. So basically what it considered is there is a stress resultant due to the traction. So like suppose if I have a beam and like it's basically it has a random cross section. So like if I take any face of the beam, then at that phase I'm only interested with the traction resultant. I don't want the traction at any point. I'm just interested in the traction resultant, and the traction resultant equals to the amount of force at the point. So like I determine this amount of force at a point, q of x at the x distance. Like this is the axis which I have. So the q of x is basically the integral of the traction in the direction of e1, like obviously traction e1 times the over the integral over the area, and this is basically the total net force which is acting on this space. And this m of x is basically the moment, which is like if I consider a p area vector, or like the p distance vector to any point on the area, then like this would be the moment which would be acting at the centroid axis, around the centroid axis. So this is the moment and this is the force. So basically now that we have moment and force, we have basically both of them in the x direction. The second thing being the conservation of mass. So the conservation of mass for this case, we basically do not assume point-wise satisfaction of the conservation of mass. That is that this gradient of sigma plus f is not equal to zero at every point, but it is equal to zero for basically an entire cross section area which we consider. So like conservation of mass, so like we, from this basically by applying the Gauss divergence theorem, so like the derivation is in the notes, but like I don't think so it's an important. So like from this conservation of mass, by like integrating it, we basically what we get is that the derivative of q of x, the force at a face, plus q is equal to zero. So like this should be equal to zero for each and every x, and where this q is basically this function, that is the integral of the traction over the boundary, and like the traction acting over the boundary. So like sum of all the tractions acting over the boundary, and this is basically the b is for the for the body forces, all the body force which basically might be acting at the area. And similarly for like the moment balance, what we have is like we consider the moment balance that p cross this thing is equals to zero. So from moment balance we get this, the derivative of moment of x plus epsilon 1 times q of x plus m is equal to zero, where m is basically the boundary condition, where like it is basically integral over the curve, like the boundary, it's basically movement due to all the traction vectors and also the movement due to all the body forces. So basically it is a set of differential equations. So like these are basically all differential equations are now in only one variable, x variable. So like we need to find out this moment of x function, and we also need to find out this q of x function. So from like we would be having this m and q values from like obviously boundary conditions which we are given. So basically our aim is to find m of x and q of x from this. So this is like basic of the beam theory. So the next thing that we considered is the kinematic hypothesis. So like kinematic hypothesis state that like any cross sections which are plane, which should always remain a plane cross section. So like it cannot be that I have this elliptical cross section, then it would be transformed into some square cross section or this. So cross section basically which are plane will always remain a plane. And like for the small rigid rotation, like if I consider a rigid rotation among the three axes, like I mean basically what we assume is that it's not deforming as such, but it's doing a rigid rotation about all the three axes. Like I mean the axes are basically being rotated, and so like we would have a new l dash axis, like where the point was originally. So like l dash is equals to l plus 3 epsilon x. Basically that's what we are currently considering. L dash is equal to l plus theta cap cross L. So like the theta cap is basically the vector of all the like the rotations which are acting in orbit. So like basically it's a two type of displacement. So one being the displacement of the centroid. So like the centroid of would like displace to some u of x. So like centroid would be at any x. So like it would be displaced to another u of x. And there's also an angular displacement. So like I mean the plane would basically do rigid rotations along its own axis. So like that would cause a change in the direction of each and every point. So that is basically angular displacement. So like basically there are two type of displacement. So like u is basically due to the plane itself moving from one direction to the another direction, and other is basically being due to the rotation occurring in the plane. So like the plane might rotate around its centroid axis basically. So these are the two ways where like how displacement might happen in this. So like we can like basically consider a point B, point D, and like there the displacement would be, as we said, the u of x would be basically where the centroid is moving. So like u of x would be centroid might move from u of x plus v of x plus w of x. So like it only depends on x direction, and like due to the rigid rotation of the cross section area, the other points on the plate would also move with respect to x. So like at every x, we have this theta of x functions, and we have this z and y coordinate of that point. So from that, we have basically the displacement field of every point. So what we have to do now is we have basically six functions of x that we have to find. So like now note that these are not three-dimensional functions. Like the u, v, and w, basically everything depends on x only now. So what we can do is now that we have this displacement field, we can calculate the strain tensor from this, and from the strain tensor we can calculate the stress tensor. So like everything is basically in terms of x. So like we don't need to perform multivariable calculus. So like we just have six functions, and now we have to find the differential equation that we can apply on these six functions to get the solution basically. So like we can basically calculate the sigma stress tensor. Like it's basically we I have like used different constant where b and c would be basically some constant of this, and so on and so forth. So basically these are the six. So like we have u, right? So from u basically you can calculate the gradient of u, and basically from there you can basically find the stress. So like once we have the stress, we can now basically find this q and rescue and movement by just basically just doing this. Like q is equals to integral of t1 over this. So like and then we can basically put it into this, because like see these are the our governing equations. Like these equations should always satisfy. So like we want to write these equation in terms of our unknowns u, v, w, theta 1, theta 2, and theta 3. So basically, we are writing this q of x, q like we know this q because we would get that from the boundary condition, and basically we have this three equations c a u double dash, and these are like equation in terms of u v w and theta two theta three, and so on. And from the moment balance equation also we have these three amount of equations. So like I don't think so we need to remember these equations, because like these are like very simple equations, and they basically are derived in the beam theory, and they are also derived in the notes. So like I don't think so it's needed, and I don't think you need to go towards it. And like it's basically, so like now that we have these three things, we have this six set of differential equation and six functions which we have. We have six function u, v, and w. We have theta 1, theta 2, and theta 3. So we need to find the six unknown functions of x. These are all functions of x, and these are the six differential equations which we have. And like qx, qy, qz would, which we would obviously get from the initial like problem, which the problem which would impose. So like basically what we can do is qx, qy, and qz we basically have from the problem specification, and we can also have this boundary conditions to like get the Dirichlet boundary conditions would imply that we have the function values at 0 or L, and the Newman boundary condition is that we have this basically entire thing that like q of x would be this and m of x would be this, and so on and so forth. So basically now that we have this six set of ODEs, and then we have this boundary conditions, so we can basically find everything for this. So like for basically different type of beams we have different types of this. So like I guess the details of on how to solve these differential equations have not been covered in this course, and which would be covered in the future course of structural mechanics. So this course was only for solid mechanics, so I don't think so more of this would be covered in this course. And So like I guess this marks the end of the course, and like this is just basically a transition to structural mechanics, which is our next course in this. And I guess this was it for this course. This was the syllabus for this course, and I guess I wish you all best of luck for the examinations for the solid mechanics examination. And I guess you kind of understood what I did in this course, and I hope that this course helped you for your preparations. And that's all I have to say. Bye.